Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Continuing Education, SOCE, Master's Degree Programs, Master of Science, Food Nutrition, MSCDFSM, Revised, Second Year, MFN04 Advanced Nutrition, Unit-1 Understanding Nutrition, 1.1 Introduction. This unit covers the scope of advanced nutrition. It begins with some definitions and basic concepts and briefly traces the history of nutritional sciences. It will make you familiar with terminologies in nutritional requirements such as minimum requirements, recommended dietary intakes, RDIs, and dietary reference intake, DRIs, terms that you will come across frequently in the other units as well. The understanding of these concepts would help you to analyze critically the various methods that are employed to study and estimate nutrient requirements. Based on considerable research, different national and international organizations have made recommendations concerning human nutrient requirements. You will learn about these and their application in different settings in the final section of this unit, Objectives. After studying this unit, you will be able to discuss the discovery of food factors necessary for the prevention of nutritional deficiency diseases and for the promotion of positive health, analyze the concept and basis of human nutritional requirements. Define basic terminologies in relation to human nutritional requirements such as minimum requirements, maintenance allowance, and recommended allowances, advanced nutrition. Explain the different methods of determining human nutrition requirements and describe the national and international recommended dietary allowances of human nutritional requirements and learn to apply them for planning and evaluating diets for health and disease. 1.2 Nutrition Science, Basic Concepts. Food is the very basis of our life. The food we eat, through the process of digestion, we know, is converted into nutrients. And these nutrients are absorbed, transported to different parts of the body and utilized for the day-to-day functioning, at the end of which they are disposed of by further metabolism and transformation into the end products. We need to consume a variety of foods in order to remain healthy. A simple thumb rule is to classify foods into different food groups. The basic 7 food groups concept is useful in getting a balanced diet that helps us to remain healthy. These basic 7 food groups are 1. Cereals and cereal products. 2. Pulses, also meat and meat products. 3. Milk and milk products. 4. Vegetables and fruits. 5. Nuts and all seeds. 6. Fats and oils. And 7. Sugars. An easy way to understand the balanced consumption of these 7 food groups is represented as 4 steps to a healthy diet as shown in Figure 1.1. Our daily diets for maintaining good health should be made up of generous amounts of vegetables and fruits, adequate amounts of cereals, pulses, milk and milk products, moderate amounts of meat and flesh foods and limited quantities of fats and oils, nuts and all seeds and sugars. Now with this basic understanding, let us get to know what we mean by nutrition science. What is nutrition science? A definition: nutrition science, simply defined, is the knowledge regarding the role of food in maintaining good health. A comprehensive definition given by Robinson runs like this: the science of foods, nutrients and other substances therein, their action, interaction, and balance in relation to health and disease, the process by which an organism ingests, digests, absorbs, transports, and utilizes nutrients and disposes of their end products. Thus, the entire gamut of what foods are needed for maintaining good health, how they are processed to provide us the wherewith to carry out our daily activities, and how the end products of the foods we ingest are eliminated constitute the science of nutrition. The next question that you would ask is what parameters can we use to define good health? Can good health also be referred to as positive health? Does it merely mean freedom from diseases or is it more than that? Let us see what constitutes good health. Positive health has been defined as not merely freedom from diseases but a state of complete physical, mental and spiritual well-being. The requirements for positive health are many and these are outlined below. 1. Achievement of optimal growth and development during childhood and adolescence, reflecting the full expression of an individual's genetic potential. Growth is defined in terms of physical features such as height and weight, while development includes all aspects of physical and mental development. 2. Maintaining structural and functional integrity of body tissues throughout life, allowing thereby to leading an active and productive life. Examples include moist, bright and sparkling eyes for good vision, smooth and soft skin that will prevent the entry of infections through the body surfaces, and similarly maintaining the integrity of internal organs like the gastrointestinal tract and the liver for proper digestion and assimilation of foods and removal of toxic waste products. 3. Ability to perform mental tasks efficiently and mental well-being. Good nutrition is essential for children to develop cognitive skills, learn school-oriented tasks well and perform optimally and stay on in school. Similarly, good nutrition is important in sustaining attention and memory in adults as well. 4. Ability to withstand the inevitable process of aging with minimal disability. 5. Ability to combat diseases and resist infections and to minimize the effects of environmental pollutants. To maintain positive health, it is essential that we combine and consume a variety of foods in such a way that the nutrient needs for the above functions are all provided. Understanding nutritional needs and translating this into practical diets is no longer a simple process, but requires a sound knowledge of nutrition. First, we need to review what are the nutritional components of the foods that we eat. The following paragraph will focus on this aspect. What are the nutritional components of the foods we consume? The foods that we consume are composed of varying quantities of the following nutritionally important components. 1. Carbohydrates. 2. Proteins. 3. Lipids. 4. Water. 5. Minerals. 6. Vitamins. 7. Fiber. Understanding nutrition. 8. Phytochemicals and antioxidants. 9. Detoxifying agents. If these nutritional components are consumed daily in the amounts and proportion required, then the chances are that we will maintain a good health. Therefore, a good knowledge and understanding of the food sources of these various nutritional components, their metabolism, and their requirements for different age and physiological groups is an essential prerequisite for maintaining good health. This course is an attempt to provide this knowledge and skills. The last 3 decades has seen a tremendous progress in nutrition. Although the importance of nutrition in growth, development, and the prevention of nutritional deficiency diseases was well recognized since the 19th century, it is only in the last 3 decades that the frontiers of nutritional science has expanded to include newer and more dimensions of health such as prevention of chronic degenerative diseases, retardation of aging and promotion of mental well-being. Human beings require a large number of nutrients, about 40, for many of which the requirements are well established. In addition, recent advances have shown that the diet components like carotenoid pigments, phenolic compounds, flavonoids, anthocyanins, lignans and indoles are bioactive compounds with a potential role in the prevention of degenerative diseases and in detoxification. The earlier dictum that if the diet provided adequate energy to meet our requirements, then it is likely to be adequate in other respects, is no longer true. We have to make conscious efforts to have a healthy diet. If you are a nutrition professional or a dietitian, then you also have the responsibility of planning diets for others both for health and in diseases, and in addition, you will be counseling a large number of people on appropriate diets. This unit will help you to do that by providing a basic understanding of nutritional requirements. We begin our study of advanced nutrition with a review of the history of nutrition and the discovery of food factors. Nutrition scenario in the Indian context is also highlighted. In the next section, 1.3 History of Nutrition, knowledge of human nutritional needs and relationship between diet and health was placed on a modern scientific footing only since the 19th century, after Lavoisier established that the body obtained energy through oxidation of foodstuffs, and Magendie recognized that protein was essential in the diet for survival. Respiration chambers for estimating energy requirements were developed by mid-19th century. Nitrogen balance studies that measured nitrogen retention reasonably accurately made it possible for the first time to estimate energy and protein requirements with some precision. Some of these experimental evidences and contributions are highlighted in box 1. 1. For your reference. The first dietary standards were proposed based on these experiments in the year 1860 that an adult human required a daily intake of food to provide 3000 kilocalories and 80 g of protein. During the next 50 years, several recommendations were made for energy and protein requirements, most of them based on the usual intakes of healthy individuals. Box 1.1 The experimental evidences and contributions. James Lind in 1747 performed controlled experiments on sailors who developed scurvy.
He divided them into different groups. The group receiving 2 oranges and 1 lemon every day showed dramatic improvements. The first demonstration that scurvy was a disease caused by dietary deficiency. The group receiving cider every day showed some improvement, other groups did not show much improvement. Lavoisier's contributions demonstrated that biological oxidation of foods within the body was very similar to combustion of foods outside, both processes utilizing O and producing CO. He introduced the concept of respiratory quotient, effect of food and exercise on metabolism. The effects of fasting, a postprandial contribution, etc. were performed by Seguin and Lavoisier and was published in 1789. Lavoisier is considered as father of modern nutrition. Unfortunately, during the French Revolution, he was executed. Another scientist, William Stark, performed experiments with simple diets on himself. He used water and bread diet, found that it was not even providing enough energy. Addition of milk, sugar, olive oil was found to contribute to better health but left him still with nutritional deficiencies, providing an indication that the science of nutrition was still in an early stage and all necessary dietary constituents for health were not known. In the 19th century, the energy contributions by carbohydrates, proteins, and fats were identified. A controversy developed whether the body can convert carbohydrates into fat, which was resolved subsequently. It was further established that carbohydrates and fats are preferred fuels, both at rest and during exercise. The body shifts from one fuel to the other depending upon the availability of nutrients. By 20th century, the role of minerals and vitamins were established by Zunen, Hopkins, and Eichmann and Funk. The term vitamin was coined by Funk by combining vital and amine.
Let us review the discovery of essential food factors and the expanding frontiers of nutrition next. 1.3.1 Identification of food factors and discovery of water-soluble vitamins. Nutritional deficiency diseases such as beriberi, pellagra, and scurvy were all known and described much before the food factors responsible for these illnesses were discovered. Beriberi is reported to be mentioned in a Chinese medical book dating back to 2697 BC, but it was only in 1926 AD it was established that this illness was due to the deficiency of a dietary factor present in rice bran. Later, this dietary factor was identified as thiamine, vitamin B. Similarly, pellagra and scurvy were rampant in the 18 and 19 trademark symbol century, but the deficient food factors responsible for these diseases, namely niacin and ascorbic acid, were identified only in the 1930s. Pellagra was first described in 1930 by Kussel in Poor Peasants Consuming Match Diet, where they associated it with infection in cereal during fermentation. But later studies showed that it is niacin deficiency which led to pellagra. The discovery of scurvy was well documented in sea voyages, and that it can be cured by consumption of fresh fruits was well established by the experiments of James. The 4 decades from 1910 to 1940 were the golden era of vitamins, when thiamine, niacin and ascorbic acid were isolated from food sources and were shown to result in complete recovery from the then widely prevalent diseases of beriberi, pellagra and scurvy. Today these diseases are no longer a public health problem anywhere in the world. Dietary recommendations made through the 1920s and the early 30s were based on limited quantitative information, but it was already recognized by the League of Nations Health Organization, as well as the U.S. Department of Agriculture, that scientific knowledge of human requirements for essential nutrients was needed to provide a reliable base for practical nutrition programs.
The Food and Nutrition Board of the National Research Council/National Academy of Sciences, NRC/NAS, of USA prepared a set of dietary standards for adequate intakes of 9 nutrients in the year 1941, which was formally adopted at a National Nutrition Conference in the same year. These were the first set of recommended dietary allowances. 1.3.2 Discovery of other essential nutrients. Following the identification of the food factors involved in beriberi, pellagra and scurvy, the search was on for other water-soluble vitamins. During the years that followed, we witnessed an expansion in the list of essential nutrients, which currently stand at about 40. These include the major energy-giving food components, namely, carbohydrates, proteins and fats, also known as the proximate principles, the water and fat-soluble vitamins, and the minerals including the trace and ultra-trace minerals. The list of currently known essential nutrients is shown in Table 1.1. Table 1.1, Currently known essential nutrients and nutritionally relevant compounds. 1. Proteins and amino acids. 2. Carbohydrates. 3. Lipids. 4. Water. 5. Sodium. 6. Potassium. 7. Calcium. 8. Phosphorus. 9. Magnesium. 10. Iron. 11. Zinc. 12. Copper. 13. Selenium. 14. Iodine. 15. Chromium. 16. Vitamin A. 17. Vitamin D. 18. Vitamin E. 19. Vitamin K. 20. Thiamine. 21. Riboflavin. 22. Nicotinic acid. 23. Vitamin B6. 24. Pantothenic acid. 25. Biotin. 26. Folic acid. 27. Vitamin B12. 28. Vitamin C. 29. Choline. 30. Carnitine. 31. Inositol. 32. Taurine. 33. Arsenic. 34. Boron. 35. Manganese. 36. Molybdenum. 37. Nickel. 38. Silicon. 39. Vanadium. 40. Fluorine. RDAs established for these by the joint FAO/WHO expert consultation.
He divided them into different groups. The group receiving 2 oranges and 1 lemon every day showed dramatic improvements, the first demonstration that scurvy was a disease caused by dietary deficiency. The group receiving cider every day showed some improvement, other groups did not show much improvement. Lavoisier's contributions demonstrated that biological oxidation of foods within the body was very similar to combustion of foods outside, both processes utilizing O and producing CO. He introduced the concept of respiratory quotient, effect of food and exercise on metabolism. The effects of fasting, a postprandial contribution, etc., were performed by Seguin and Lavoisier and was published in 1789. Lavoisier is considered as father of modern nutrition. Unfortunately, during the French Revolution, he was executed. Another scientist, William Stark, performed experiments with simple diets on himself. He used water and bread diet, found that it was not even providing enough energy. Addition of milk, sugar, olive oil was found to contribute to better health but left him still with nutritional deficiencies, providing an indication that the science of nutrition was still in an early stage and all necessary dietary constituents for health were not known. In the 19th century, the energy contributions by carbohydrates, proteins, and fats were identified. A controversy developed whether the body can convert carbohydrates into fat, which was resolved subsequently. It was further established that carbohydrates and fats are preferred fuels, both at rest and during exercise. The body shifts from one fuel to the other depending upon the availability of nutrients. By 20th century, the role of minerals and vitamins were established by Zunen, Hopkins, and Eichmann and Funk. The term vitamin was coined by Funk by combining vital and amine. 13.3 Expanding frontiers of nutrition. While the essential nutrients mentioned in Table 1.1 are indispensable and our diets need to provide them all in adequate quantities, it has become clear that for healthy living they are not by themselves enough. Other dietary constituents, such as the phytochemicals and antioxidant substances, are equally important. A deficiency of these may not produce overt recognizable symptoms, but they are nevertheless known to play an important role in prevention of degenerative diseases, delaying the adverse and often considered as inevitable consequences of aging like cataracts, blunted memory, and in the detoxification of waste materials or environmental pollutants. The present data is sufficient to include these as essential dietary components, but what is lacking is the information concerning the amounts of these compounds that we need to consume in our daily diet. While on the topic of history of nutrition and expanding frontiers of nutrition, let us also look at the developments in the nutrition scenario in India. 1.3 Point for the Indian nutrition scenario. Nutrition research in India was pioneered by Dr. Robert Mac Carrison. His works on beriberi and gained attention on the interlinks between nutrition and health. Further, nutrition research laboratories, NRLs, were established in Coonoor in southern India in 1929, a time when the three nutritional deficiency diseases, mainly beriberi, scurvy and pellagra, were occupying the attention of nutrition scientists everywhere. Notable British scientists such as Dr. Passmore made significant contributions in the initial 10 years. Dr. Wallace Ackroyd, as the director of these laboratories, contributed meaningful research for improving the nutritional status of vulnerable groups in India. Information on nutritive value of Indian foods was first published in 1937 by Dr. Ackroyd. This booklet, popularly known as Health Bulletin No. 23, has undergone several revisions and currently is the best-known resource to nutrition scientists as far as the nutritive value of Indian foods are concerned. Following this, an excellent tradition of nutrition research primarily focused on finding solutions to our major nutritional problems has been developed and passed on to the present generation by stalwarts like Dr. V.N. Patwardhan, Dr. C. Gopalan, Dr. V. Ramalingaswamy, and Drive S. G. Sirkansha, to name a few. The NRL was shifted to Hyderabad in 1966 and was renamed as National Institute of Nutrition (NIN), an apex body administered by the ICMR that coordinates nutrition research in India. Recent advances in cellular and molecular biology have opened new avenues for research in nutrition. Various interactive fields have been developed between nutrition, on one hand, and immunology, neurosciences, genetics, etc. on the other as the major thrust areas for understanding the major nutritional problems of the country, and contributing to meaningful research. Thus, NAN, along with other research institutions, is developing locally relevant solutions to combat various nutritional disorders in the country. Major contributions have been on iron deficiency anemia, vitamin A control program, fluorosis, lathyrism, iodine deficiency disorders, IDD. To combat 4 major losses, fortification programs are being developed. This has been achieved because of the major understanding about the physiological role of a nutrient and its metabolic influences on health. The history of nutrition reviewed above is summarized here with under points to remember. Do read them carefully. Points to remember: history of nutrition. The first recommendations for energy and protein requirements were made in the year 1826. The years 1910 to 1940 witnessed the discovery of thiamine, niacin, ascorbic acid, and several other water-soluble vitamins and led to the dietary prevention of beriberi, scurvy, and pellagra. The last 3 decades of the 20th century has ushered in a new era of expanding frontiers of nutrition, with a major focus on diet as the sheet anchor of prevention of age and lifestyle-related chronic degenerative diseases. With this basic review of history of nutrition, we shall now turn our attention towards understanding the basic concepts of human nutritional requirements. 1.4 Nutritional requirements. Nutritional requirements are defined as intake levels of nutrients that meet specified criteria of adequacy, such as normal growth, prevention of deficiency, signs, and maintenance of tissue pools of nutrients, and at the same time, preventing the risk of deficiency or excess. The concepts in relation to human nutritional requirements are defined next in this section. 1.4.1 Definition of concepts in relation to human nutritional requirements. In this subsection, we will understand a few basic concepts that are related to nutritional requirements. Go through these carefully and understand the concept. As you proceed further, A. Probability concept of requirements versus risk of deficient and excess intake. Figure 1.2 best illustrates the concept of a requirement for an essential nutrient. The relationship between the level of intakes and the probability that the intake is deficient or excess is portrayed in this figure. As you may have noticed, the estimated average requirement, R, is the intake at which the risk of the inadequacy is 0.50% to an individual. The intake at which the risk of inadequacy is judged to be essentially 0 is taken as the requirement for that nutrient. As the intake rises above this level, a point is reached when risk of excess exceeds 0. The range between the intake level at which risk of deficiency is 0 and the point at which the risk of excess rises above 0 is taken as the safe range of intakes. This concept is utilized in deriving the recommended dietary intakes, RDAs, and the upper intake level, UL, for all the nutrients except energy. Why this concept is not used in deriving energy requirements is discussed in Unit 2 on energy requirements. Look at the screen dash, Figure 1.2, relation between level of dietary intake of an essential nutrient and probability that intake is inadequate or excess. Having understood the probability concept of requirements, let us now turn our attention to other factors that are determinants of nutrient requirements. B. Age, sex and body weight are the determinants of nutrient requirements. Age, sex, and the body weight influence nutrient requirements. Let us see how age requirements change with increasing age. Between birth and maturity, nutrient requirements per unit body weight are higher during growth and they decrease after growth has ceased. For e.g., the energy requirement of an infant is 103 kilocalories per kg body weight, while for a sedentary adult male it is only 38 kcal per kg body weight. Similarly, the protein requirement for an infant 9-12 mths is 1.5 g per kg, while that of an adult is 1 g per kg body weight. Requirements increase during pregnancy as the fetus grows. In lactation, the requirements increase in proportion to the amount of milk secreted. At age of 40 and beyond, there is a decline in the lean body tissue and a decline in activities, both of which result in a decline in the energy requirements. However, this is not accompanied by a reduction in the nutrient requirements due to a reduced efficiency of gastrointestinal function with aging. We will learn more about these issues later in this course. Sex. There are some differences in requirements between the two sexes, however, except for iron, these are apparent rather than real, as the differences disappear when the requirements are expressed per unit of body weight. In the case of iron, between menarche and menopause, the iron requirements of females understanding nutrition are more than that of males due to menstrual losses of blood in women. Body weight requirements are considered to be a function of body weight for individuals who are not overweight. However, for some nutrients, requirements are not proportional to body weight. The general procedure for those who deviate from the normal weight is to adjust the requirements to their actual body weights. For overweight and obese individuals, lean body weight may be used instead of the total body weight. Related to the concept of requirements being a function of body weight is the concept of defining a reference man and a woman, reference man and reference woman. The reference man and woman are defined as points of reference only. For Indians, a reference man is defined as a man between 19 to 39 years of age, with a body weight of 65 kilograms, free from disease and physically fit for active work. On each working day, he is engaged for 8 hours in an occupation that involves moderate activities. While not at work, he spends 4 to 6 hours sitting and moving about, 2 hours in active recreation and 8 hours in sleep. A reference woman is defined as a healthy woman of 19-39 years, with a body weight of 55 kilograms, engaged for 8 hours in an occupation involving moderate activities, and while not at work spends 4 to 6 hours sitting and moving about, 2 hours in active recreation and 8 hours in sleep. Nutrient requirements are defined for the reference man and woman, and for those who deviate from the reference man and woman, adjustments are made for the different body weights. Table 1.2a and 1.2b presents the RDA and EAR4 different nutrients for Indians. ICMR 2020. Besides age, sex and body weight, there are other factors which influences the requirement, which are highlighted next. C. Individual variability of requirements. Nutritional requirements, like many other biological characteristics, vary for different individuals, arising due to inherent differences between individuals. 2 adult men with the same body weight can have different requirements for energy and other nutrients. The distribution of requirement for proteins of adults is illustrated in Figure 1.3. This distribution is called Gaussian or normal distribution. We have only limited data on the distribution of nutrient requirements, therefore, it cannot be said that all requirement distributions follow the normal distribution as illustrated in Figure 1.3. Iron requirements for females, for example, are a highly negatively skewed distribution, portraying the likelihood that a given level of usual intake is inadequate to meet the true needs, as shown in Figure 1.4. However, in the absence of adequate data for many nutrients about the requirement distribution, an assumption is made that for all nutrients except iron, the requirements are normally distributed, i.e., they follow a Gaussian distribution. Figure 1.3, protein requirement for men 15. Look at the screen. When the requirement distribution is normal, the quantitative requirement for a nutrient for 95% to 99.9% of individuals in a population group fall between the mean 2.d and mean 3. SD. Refer to Figure 1. 5. As the normal distribution is symmetrical, 50% of individuals in a group will have requirements below the mean, and another 50% will have requirements above the mean. Individual variability is often expressed as coefficient of variation, CV, that is, standard deviation expressed as a percentage of the mean. For most biologic variables, including nutrient requirements, CV is about 15%. Based on the above properties of the normal distribution, you can see that the quantitative nutrient requirements of practically all individuals in a specified life stage and gender group will be covered by the mean 2SD. This concept is used in deriving the recommended dietary allowances and safe levels of requirements. Next, let us study about bioavailability as a factor influencing requirements. D. Bioavailability of nutrients. The amount of many nutrients needed in the diet depends on the absorption or bioavailability of the nutrients. Bioavailability is defined as the percent of the dietary nutrient absorbed and utilized for a specific function by the body. The percent absorption varies widely for different nutrients depending on the quantities ingested and the presence of other constituents of the diet. Examples are iodine absorption is nearly 100%, calcium absorption in a normal adult is about 40% to 60%, while that of iron varies from 1% to 15%, depending on the type of iron and other constituents of the diet. The concept of bioavailability is best illustrated by iron. Iron is present as inorganic iron in vegetarian foods and as organic iron in meat and flesh foods. The inorganic form of the iron, as you may already be aware, is known as non-heme iron, while the organic form is known as heme iron. The non-heme iron absorption is affected by several constituents of the diet, while heme iron absorption is relatively independent of these constituents, as you would learn later in Unit 10 of this course. The dietary constituents that inhibit non-heme iron absorption are many phytates, present in the outer layer of cereal grains, tannins in tea, calcium in foods, and oxalates in leafy vegetables, are all inhibitors of iron absorption and reduce the absorption from a vegetarian diet. On the contrary, vitamin C present in fruits and vegetables and sulfur-containing amino acids and a factor in meat and flesh foods enhance iron absorption. The net absorption of iron from a vegetarian diet depends on the relative amounts of the inhibitors and enhancers in the diet. If the diet is predominantly vegetarian and has high amounts of inhibitors, the absorption of iron may be as low as 1%, and if the proportion of enhancers is high, the absorption could rise to 5 to 10%. The recommended amounts of nutrients include a correction for bioavailability, wherever relevant. Having gone through the discussion above, we hope the few basic concepts that are related to nutritional requirements must be clear and well understood. Next, we shall review a few basic terminologies that you would come across while studying about nutritional requirements. 1.4.2 Basic terminology in relation to nutritional requirements. By now you would have a good understanding that nutrient requirements are affected by a number of factors, and in order to have adequate nutrient intakes, these factors have to be taken into consideration for different population groups. You will recall that earlier we defined positive health as not merely freedom from diseases but a state of complete physical and mental health. In a similar manner, nutrient requirements should be such as to promote optimum health rather than merely to prevent nutritional deficiency disease. There are differences in the level of requirements for prevention of deficiency diseases vs. promotion of positive health. Let us now get familiar with the basic terminologies to describe these. Minimum requirement. Minimum nutrient requirement is defined as the lowest amount of the nutrient from the diet that will prevent clinically detectable impairment in function. For example, it has been established through experimental studies that an intake of 40 mg of ascorbic acid will prevent the occurrence of scurvy in individuals, and therefore the minimum requirement of ascorbic acid is 40 mg per day. However, it is highly undesirable to subsist on minimum requirement on a continuing basis. We should strive on a daily basis to meet the lowest intakes that would assure positive health rather than merely protect us from frank nutritional disease. In other words, we should strive for the safe level or the RDA rather than the minimum requirement, maintenance requirement. This is defined as the amount of nutrient that is needed to replace the wear and tear of the tissues within the body in a healthy individual. This does not take into account the need for growth or for replacement of body tissues in a person recovering from illness. Safe requirement. Given the individual variations in nutritional requirements that have been discussed earlier, the lowest continuing intake level of a nutrient to satisfy Good health varies from one individual to another. In practice, we want to set up requirements that would meet the needs of most people and will be safe at the same time for all. For defining the safe requirement, we use the statistical probability concept that was defined earlier in subsection 1.4.1 and in figure 1.2. The lower and upper limit of the range of intake in which the risk of inadequacy, as well as the risk of excess is zero, is taken as the range of safe requirement, subsistence allowance. These estimates are also called survival requirements and are of value during emergency or natural calamities such as earthquakes, etc. Hence, when there is a crisis and whole population is involved, the people are fed on such allowance. Such an intake allows only minimum movement and is not compatible for long-term health and makes no allowance for the energy needed to earn a living or prepare food. Long intake of diets of such value shows deficiency as the minimum requirements are not met, and hence can prove to be fatal. Recommended dietary allowances, RDA. The recommended dietary allowances are defined as the daily dietary intake level that is sufficient to meet the nutrient requirements of nearly all healthy individuals in a particular life stage and gender group. The RDA is derived from the statistical distribution of requirements for nutrients. It is generally assumed that nutrient requirements are distributed normally. With this kind of distribution, as already mentioned in subsection 1.4.1, the requirements of 97 to 98% of individuals in a given population group will be below the mean plus 2 standard deviations. Thus, mean 2SD will cover the requirements of practically all individuals in that population group and is designated as the RDA for that particular nutrient. This approach is used for deriving the RDA for all nutrients except energy. The RDA is intended for use primarily as a goal for usual intakes. Recommended nutrient intakes, RNIs, is another term commonly used to describe nutrient requirements and is equivalent to RDA. Dietary reference intakes, DRIs, are relatively new to the field of nutrition. The DRIs are a set of 4 nutrient-based reference values that can be used for planning and evaluation of diets of individuals and population groups, and are meant to replace the former RDAs of the US and RNIs of Canada. The DRIs are different from the RDAs and RNIs in 3 respects. These include 1. Where specific data on safety and efficacy exist, reduction in the risk of chronic, degenerative diseases is included in the formulation of the reference intakes, rather than using only the absence of signs of deficiency. 2. Where data are adequate, upper levels of intake to prevent adverse consequences of excess are established, i.e., the upper levels will tell you not to exceed these at usual intakes, and 3. Components of food that may not fit the traditional concept of an essential nutrient but nevertheless are shown to have beneficial effects for human health are reviewed, and if data permit, DRIs are established for these. The 4 nutrient reference values are described below. A. The estimated average requirements, EAR, considering that the nutrient requirements follow a normal distribution. The EAR is defined as the average daily nutrient intake that meets the requirement of half of the healthy individuals in a given life stage and gender group. Note, earlier RDA has used mean rather than the median. At this level, the other half of the individuals will not meet their requirements. The EAR is based on specific criterion of adequacy, derived from a review of the literature. Reduction of disease risk is considered along with other health parameters in the selection of this criterion. EAR is used to calculate RDA. B. RDA. The RDA is the average daily dietary intake that is sufficient to meet the nutrient requirement of nearly all healthy individuals in a particular life stage and gender group. Under assumption of normality of the distribution of requirements, the RDA can be calculated from the EAR and the standard deviation of requirements as follows. Recommended dietary intake equals estimated average intake 2SD requirement. The RDA is intended to be used as a goal for usual intakes from the diet. Since RDA is established from EAR, if data are inadequate to estimate the EAR, no RDA can be established. In such cases, the adequate intake AI, as described next, is used as the goal. See adequate intake AL if sufficient data are not available to establish an ER, and hence RDA, the AI is derived instead. The AI is derived from observations of nutrient intakes by a group of apparently healthy individuals who are maintaining a defined nutritional state or criterion of adequacy. Criteria of adequacy include normal growth, maintenance of normal levels of nutrients in plasma or general health. The mean observed intake of this group of healthy individuals of a particular life stage and gender is taken as the AI. While AI can be used as a goal for individual intake, it has only limited use in assessment. As and when more data become available, the AI will be replaced with RDAs. It must be noted here that AI represents an informed judgment about what appears to be an adequate intake for an individual based on available information. On the other hand, RDA is data-based and is a statistically relevant estimate of the required level of intake of the nutrient for almost all individuals. For this reason, AI must be used with caution. D. Tolerable upper level, TUL. The TUL is the highest continuing level of daily nutrient intake that is likely to pose no risk of adverse health effects in almost all individuals in the specified life stage group. Note, the TUL is not intended to be a recommended level of intake. It serves the purpose of warning people that levels higher than UL are going to be associated with adverse health effects and therefore should be avoided. Table 1.3 present the TUL for nutrients, ICMR 2020. In the case of macronutrients, there is an additional category of recommendation, namely acceptable macronutrient distribution range, AMDR. There is evidence to suggest that an imbalance in macronutrients, e.g., low or high % of energy, particularly with certain fatty acids and relative amounts of fat and carbohydrates, can increase risk of several chronic diseases. Hence, acceptable macronutrient distribution ranges, AMDRs, have been estimated for individuals. What is the concept of AMDR? Highlight 1.2 presents a brief review. Highlight 1.1 Acceptable macronutrient distribution ranges, AMDRs, definition and basic concept. Acceptable macronutrient distribution ranges, AMDRs, are defined as a range of intake for a particular energy source that is associated with reduced risk of chronic diseases, e.g., coronary heart disease, CHD, obesity, diabetes, and/or cancer, while providing adequate intakes of essential nutrients. AMDRs have been set for carbohydrate, protein, fat, and N6 and N3 polyunsaturated fatty acids, based on evidence from intervention trials, with support of epidemiological evidence. The major nitrogenous compound of
Table
protein
1.4,
metabolism
which
is urea,
presents the
that is
recommendations
primarily
for
AMDR
in the urine.
for selected nutrients.
The vitamins
Table
are converted
1.4,
into incompletely
acceptable
oxidized
macronutrient
forms, while the
distribution
minerals like
ranges,
Ca
AMDR,
are excreted
by
as
age
such.
and physiological
We can study
groups
the amount
as
of the
percent
nutrient
energy
ingested and the amount excreted
in Table
from
1.4,
which the nutrient
you would have
balance
noticed
can
that
be
the
calculated
AMDR
as
of a
follows.
macronutrient
Amount of
is
nutrient
expressed
ingested,
as a
amount
percentage of
excreted
total
equals
energy
amount
retained,
retained,
because its
the balance
requirement
is usually
not
zero in adults
independent
and
of
positive
other
in
energy
growing
fuel
children,
sources,
indicating
or of the total energy
replacement of wear
requirement
and
of
tear needs
the
in adults,
individual,
and retention for growth
each
and
must be
tissue
expressed in
development
terms relative of the other.
children.
Using
Another
this concept,
key
we can
feature
study
of
the
each
lowest
AMDR
average
is that it
intake
has
that
a
is
lower
necessary
and upper
to
boundary.
maintain
For
zero
example,
balance in
the
adults,
AMDR
that will
for
represent the
carbohydrates
maintenance
ranges from
requirement.
40 to
Maintenance
60%
of protein
of
total
requirements
energy
have been
intake
estimated
for
this
children
way.
1 to 2 years.
Calcium balance.
If
The
the
child
child have been
consumes
performed
below
to arrive
or above
at the
this
requirements
range,
for
there
calcium,
is a potential for increasing risk
use
of
chronic
isotopically
diseases
labeled
shown to affect
nutrients,
long-term
nutrient
health,
turnover,
as well
radioactive
as
labeled
increasing
nutrients
the risk
are
of
used to know
insufficient
the total
intakes
body
of
pool
essential
and the
nutrients
compartment in which it is stored.
It is also to be noted that
The
these
pool that
ranges
falls
are also
below a
based
certain
on
level
adequate
shows
energy
deficiency.
intake.
These
and
are used
physical
to estimate
activity
how
to
much
maintain
nutrient
energy
is
balance
lost on a daily
The
basis.
concepts discussed above
Let
are
us
summarized
consider
in the
an
points
example
to
of
remember
iron
below.
isotopically labeled iron
Read
has
them
been
carefully.
used in estimating
Points
the
to
iron
remember.
requirements for
Concepts
different
and definitions
groups in relation to nutrient
Ingested
requirements.
iron is absorbed
1.
and
The
incorporated
probability
into red
concept
cells.
describes the relationship between
Complete
the levels
incorporation
of intake
occurring
and the
in
probability
15
of
days'
risk
time.
of inadequate and
A
excess
small
intakes.
dose of radio-labeled iron is
2.
mixed with
the range
diet,
of intake
and 2
in which there is
measurements
zero
are made.
probability
The
of
basal
risk of
radioactivity
deficiency
of the blood
and
risk of excess is known as the safe requirement and radioactivity of red cells after 15 days of ingesting the diet of nutrient from the retained radioactivity. 4. Nutrient requirements and vary for different individuals due to genetic differences. 6 obligatory losses of nutrients. The individual variations are described by the term coefficient, defined as the variation that occur when an standard deviation is put on a diet free of that mean requirement. 5. Mean 2SD is the recommended allowance for a nutrient, which meets the needs of 97 to 98% of the individuals in a life stage and gender group. For energy only, the mean is taken as the RDA. 6. Bioavailability of nutrients must be taken into account while making recommendations for nutrient requirements. 7. The basic terms used in relation to nutrient requirements are minimum requirements, safe allowances, recommended dietary allowances, dietary reference intakes. With a basic understanding on nutrient requirements, next we shall study the several methods used for estimating the nutrient requirements. 1.5 Methods for studying the nutrient requirements. Several methods have been used for studying the nutrient requirements. They range from observational methods like population survey of dietary intakes to experimental methods involving nutrient balance and nutrient turnover. These are described herewith. 1.5.1 Population survey of dietary intakes of nutrients. The basis of this method rests on the premise that average dietary intake of nutrients by healthy members of a group of individuals at a specific life stage and gender represents the requirement of this group. This was the only method available for a long time to estimate the nutrient needs. All early recommendations were based on this method. The limitations of the method are that since the average is calculated from usual intakes of healthy individuals eating to appetite, the method can both over or underestimate the requirements. The limitation of this method is best illustrated by the early recommendations for protein. The first ever recommendation that was formally adopted put the protein requirement of adult man as 80 g per day. Some years later, Chittenden, a German nutrition scientist based on experiments on himself, recommended that for good health, an adult man required no more than 50 g protein per day. 1.5.2 Growth studies. Nutrient requirements of infants and young children are estimated by studying the rate of growth of healthy children and the deposition of nutrients in the body. Estimation of protein needs of children is an example of this method. The weight gain of infants and children and the nitrogen content of the body at different ages are used in estimating the protein needs of children. 1.5.3 Depletion and repletion studies. This is an experimental procedure in which volunteer subjects are kept on a diet devoid of a particular nutrient until such a time when they develop overt clinical signs of deficiency of the nutrient. The lowest level of the nutrient that reverses the clinical symptoms in all volunteer subjects is the minimum requirement for that nutrient. The minimum requirement for some B vitamins and ascorbic acid has been determined through this method. 1.5.4 Nutrient balance studies. The ingested nutrients are metabolically converted into end products that are eliminated from the body through urine, feces, and sweat. Some of the nutrients are extensively catabolized while others may undergo minimal changes. For example, dietary proteins are converted into nitrogenous compounds and eliminated. The major nitrogenous compound of protein catabolism is urea that is excreted primarily in the urine. The vitamins are converted into incompletely oxidized forms while the minerals like Ca are excreted as such. We can study the amount of the nutrient ingested and the amount excreted from which the nutrient balance can be calculated as follows: amount of nutrient ingested, amount excreted equals amount retained. The balance is usually 0 in adults and positive in growing children, indicating replacement of wear and tear needs in adults and retention for growth and tissue development in children. Using this concept, we can study the lowest average intake that is necessary to maintain zero balance in adults that will represent the maintenance requirement. Maintenance of protein requirements have been estimated this way. Calcium balance studies have been performed to arrive at the requirements for calcium. 1.5.5 Use of isotopically labeled nutrients. Nutrient turnover. Radioactive labeled nutrients are used to know the total body pool and the compartment in which it is stored. The pool that falls below a certain level shows deficiency. These are used to estimate how much nutrient is lost on a daily basis. Let us consider an example of iron. Isotopically labeled iron has been used in estimating the iron requirements for different groups. Ingested iron is absorbed and incorporated into red cells. Complete incorporation, occurring in 15 days' time. A small dose of radio-labeled iron is mixed with the diet, and 2 measurements are made: the basal radioactivity of the blood before ingesting the radio-labeled diet and radioactivity of red cells after 15 days of ingesting the diet. From the retained radioactivity, the amount absorbed and requirements are calculated. 1.5.6 Obligatory losses of nutrients. Obligatory losses of nutrient are defined as the losses that occur when an individual is put on a diet free of that nutrient. For example, when we are on a protein-free diet, we continue to lose protein in the form of urinary urea and other nitrogenous compounds. Within 5 to 6 days on a protein-free diet, the total nitrogen losses as urea and other compounds stabilize to a low and constant value. The amount of dietary protein needed to replace these losses has been experimentally determined. These represent the maintenance requirement for protein in an adult. This method, however, has been discarded as it represents a non-physiological state. The various methods discussed above are summarized in points to remember herewith. Points to remember. Methods for studying the nutrient requirements. 1. Population survey of nutrient intakes of healthy individuals is one method of estimating nutrient requirements. The average intake by healthy individuals in a particular life stage and gender group represents the requirement for that group. Currently, this method is used only when there is not adequate data on requirement distribution in population groups. 2. For infants and children, growth and body weight gain has been used along with the nutrient composition of body tissues to arrive at the nutrient requirements. 3. Experimental methods such as depletion and repletion of nutrients and nutrient turnover studies have helped in determining the minimum requirements and recommended allowances. 4. Some methods like the obligatory losses which were used at one time for estimating the maintenance requirements of nutrients are no longer in use, as they represent a non-physiological state. Now that we have understood about the nutrient requirements and how they are estimated, let us get to know about the national and the international recommendations for the nutrient requirements. 1.6 National and International Recommendations for Nutrient Requirements. Various nutrition institutes and research and professional organizations in India and all over world have given recommendations for the nutrient requirements for their population groups and for people of all ages. Let us review some of these recommendations. 1.6.1 Recommendations for Indians by the Indian Council of Medical Research (ICMR). The Indian Council of Medical Research in its recent report of the Expert Group, 2020, Nutrient Requirements for Indians Recommended Dietary Allowance and Estimated Average Requirements, has made recommendations for energy, protein, fat, minerals, namely phosphorus, magnesium, sodium and potassium, iron, zinc, copper, chromium and manganese, selenium and iodine. Fat-soluble vitamin, vitamin A, vitamin D, vitamin E, K, and 7 water-soluble vitamins, namely thiamine, riboflavin, niacin, ascorbic acid, vitamin B, folate and vitamin B. These are shown in Table 1.2a, 1.2b, and 1.2c earlier. The recommendations are made for different life stages and gender groups separately. These RDAs have been derived from average nutrient requirements for each group, estimated by one of the methods mentioned under Section 1.5. The RDA takes into account the variation that exists between individuals by choosing a level that is 2 standard deviations higher than the average requirement, so that the requirements of 97 to 98% of individuals in a given age, sex, and physiological group are met. It thus aims at meeting the requirements of nearly all individuals in a population group. This approach, however, is not used for energy requirements. The average requirement for energy is taken as the RDA. The reason for this is that consumption of other nutrients in excess of requirement to the tune of 2 SD is not associated with any adverse effects, whereas consumption of energy even in small excess over requirement for a period of time can lead to overweight and obesity. The RDA also takes into account nutrient bioavailability, as in the case of iron. The bioavailability of iron in Indian diets is low, and the RDAs for adult men, children, and adolescent boys are based on 5% absorption and 8% absorption for all women. The underlying principle of all RDAs is worth recalling here again. The RDAs are meant to be used as a goal for dietary intakes on a continuing basis, so that practically all individuals in a life stage and gender group will be protected from inadequate intakes of nutrients and thus would be in a position to maintain good health. The RDAs are not meant to be used as a standard for determining whether an individual requirement has been met. Individuals with intakes lower than the RDA are not necessarily at risk if their requirements are less than the RDA, which they are for many. 1.6.2 FAO/WHO Expert Committee Recommendations. The FAO/WHO/UNU Joint Expert Committee makes recommendations for nutrient requirements periodically, revising them as and when more data becomes available. The most recent recommendations on vitamin, mineral requirement, and energy requirements were published in 2002 and 2004, respectively. We will learn about the energy requirements in the next unit, along with the WHO/FAO/UNU recommendations. We have also reviewed the dietary reference intake for population groups in US and Canada and provide valuable information on upper intake limits in the next subsection. 1.6.3 Dietary reference intakes for US and Canada. Dietary reference intakes has been published by the National Academy Press 4, the Food and Nutrition Board, and the Institute of Medicine, Washington, D.C., USA. For those of you interested in knowing about the recommendations, these tables are included in Annexure 1 at the end of this course for your reference. These are meant to be used as goals for intake in North America. For nutrient-based values are defined, these are estimated average intake, recommended dietary allowances, adequate intake, and tolerable upper levels as described earlier in subsection 1.4.2. The EAR and RDA carry the same meaning as the average intake and RDA of the Indian reference values. Also, the recommended nutrient intakes of FAO/WHO and RDA of the DRI are similar in concept. Points to remember given next summarizes the information presented in this section, so read it carefully. For further information on these recommendations, you may want to look up the following website: http://www.iom.edu/object.file/master/21/372/0.pdf. 1. The Indian Council of Medical Research has formulated recommended dietary allowances for the following nutrients for different age, sex, and physiological groups: energy, protein, fat, calcium, iron, vitamin A, thiamine, riboflavin, niacin, pyridoxine, ascorbic acid, folic acid, vitamin B2. These recommended allowances for all nutrients except energy are the mean requirement 2 SD, keeping in line with the probability approach. 3. The other two sets of recommended allowances described in this section are the ones by the joint FAO/WHO expert group and the dietary reference intakes for USA and Canada. The nutrient requirements described as RDA serve several purposes and are used by the food and agricultural ministries in different countries quite extensively. As a student, you may be looking at these requirements for evaluating intakes at the community or population level, but the application of RDA goes beyond this. We will tell you something about the application of RDAs in the next section. 1.7 Goals of National and International Requirement Estimates and RDAs. One of the goals of the RDAs has been reiterated through this unit. They serve as the guidelines for continuing dietary intakes that healthy people should strive for on a day-to-day basis in order to maintain good health. Apart from this, there are other goals.